Hi, good day. Let us learn about identifying redox reactions. In general, all chemical reactions can be assigned to one of two classes. In oxidation-reduction or redox reactions, electrons are transferred from one reacting species to another. In all other reactions, no electron transfer occurs. For example, double replacement reactions and acid-base reactions are not redox reactions. Many single replacement reactions, combination reactions, decomposition reactions, and combustion reactions, however, are redox reactions. Can you write a balanced equation for each reaction shown? The first figure shows potassium metal reacts violently with water to produce hydrogen gas, which ignites, and potassium hydroxide. Is this a redox reaction? Zinc metal reacts vigorously with hydrochloric acid to produce hydrogen gas and zinc chloride. Is this a redox reaction? You can determine whether a reaction is a redox reaction by using oxidation numbers to keep track of electrons. If the oxidation number of an element in a reacting species changes, then that element has undergone either oxidation or reduction. Therefore, the reaction as a whole must be a redox reaction. Consider this example. During an electrical storm, oxygen molecules and nitrogen molecules in the air react to form nitrogen monoxide. The equation for this reaction is N2 plus O2 will yield 2 moles of NO. Is this a redox reaction? How can you tell? Does the oxidation number of either reacting species change? If so, what is the change? Various other changes often signal that an oxidation-reduction reaction has taken place. One such change is a change in color. For example, let us look at this figure. When a colorless aqueous solution of bromide ions is added to a purple aqueous solution of permanganate ion, the solution changes from purple to pale brown. As the following unbalanced equation shows, bromide ions are oxidized to bromine, and permanganate ions are reduced to manganese 2 ions. Color changes can do more than signal that a redox reduction has taken place. They can help obtain quantitative information about concentrations in redox reactions. The titration of reducing agents and oxidizing agents is similar to the titration of acids and bases. For example, the titration of the reducing agent oxalic acid with a solution of unknown concentration of the oxidizing agent potassium permanganate is illustrated in this figure. To obtain a quantitative result in such a titration, a balanced equation of the redox reaction is required. A known mass of colorless oxalic acid is dissolved in dilute sulfuric acid in the reaction flask. The concentration of the purple potassium permanganate solution can be calculated from the volume added to reach the endpoint, which is reached when all the oxalic acid is oxidized and the next drop of purple potassium permanganate remains unreacted. The net ionic equation for the reaction can be written. From this equation, the oxidation number changes for the oxidized and reduced species can be determined. The full balance equation for this reaction is 2 moles of potassium permanganate plus 5 moles of oxalic acid and 3 moles of sulfuric acid will yield 2 moles of manganese sulfate, 1 mole of potassium sulfate, 10 moles of carbon dioxide, and 8 moles of water. Let us have this sample problem. Use the change in oxidation number to identify whether each reaction is a redox reaction or a reaction of some other type. If a reaction is a redox reaction, identify the element reduced, the element oxidized, the reducing agent, and the oxidizing agent. The first step to solve this problem is to analyze. Plan a problem-solving strategy. Use the rules to assign oxidation numbers to each element. Note whether there are any changes in oxidation number. If there are, the reaction is a redox reaction. The element with an oxidation number that increases is oxidized and is the reducing agent. The element with an oxidation number that decreases is reduced and is the oxidizing agent. The second step is to solve. Apply the problem-solving strategy. Let us answer number 1. 1 mole of N2O4 will yield 2 moles of NO2. In the reactant, nitrogen has an oxidation number of 4+, while oxygen is 2-. In the product, nitrogen has an oxidation number of 4+ and oxygen 2-. This is a decomposition reaction. Neither oxygen nor nitrogen changes in oxidation number. Therefore, the reaction is not a redox reaction. For the second equation, when chlorine reacts with 2 moles of sodium bromide, the products are 2 moles of sodium chloride and bromine. The oxidation number of chlorine in the reactant is 0, while sodium is 1+ and bromine is 1-. In the product, sodium has a charge of 1 positive, while chlorine has a charge of 1 negative, and bromine is 0. This is a single replacement reaction. The chlorine is reduced. The bromide ion is oxidized. This is a redox reaction. Chlorine is the oxidizing agent. Bromide ion is the reducing agent. The third step to solve this problem is to evaluate. Do the results make sense? Only in redox reaction do the oxidation numbers of reactants change as product form. Only reaction B represents a redox reaction. In B, each chlorine atom accepts an electron from a bromide ion. The chlorine molecule is reduced to 2 chloride ions. Therefore, it is the oxidizing agent in the reaction. That makes sense because chlorine is more electronegative than bromine and thus more apt to gain electrons. Because the bromide ions are oxidized to molecular bromine, the bromide ions are the reducing agent. If this is your first time watching my videos, make sure you hit the subscriber button. Thank you for watching.